Welcome to the fifth session of this exponential and logarithmic function series. In this session, we will demonstrate more advanced analytical skills to solve exponential and logarithmic equations, as well as their inequalities through more challenging worked examples.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the fifth session of this exponential and logarithmic function series. In this session, we are going to demonstrate more advanced techniques to solve exponential and logarithmic equations, as well as their inequalities through 6 worked examples. The question in example 1 is to compare two modulus logarithmic expressions given that x is between 0 and 1 and the base a is greater than 0 but is not equal to 1. Here we are going to present two approaches to answer this question. As for the first approach, we start by assuming y equals the difference between the two modulus logarithmic expressions. We make it equal to the modulus of logarithm base a of 1 minus x minus the modulus of logarithm base a of 1 plus x. The next step is to discuss the outcome of y based on the value range of a. When a is between 0 and 1, logarithm base a of 1 minus x is greater than 0, while logarithm base a of 1 plus x is less than 0. Hence, y equals logarithm base a of 1 minus x plus logarithm base a of 1 plus x, which is greater than 0. When a is greater than 1, logarithm base a of 1 minus x is less than 0, while logarithm base a of 1 plus x is greater than 0. Hence, in this case, y equals negative logarithm base a of 1 minus x minus logarithm base a of 1 plus x, which equals negative logarithm base a of 1 minus x squared, which is greater than 0. We may conclude from the above that y is greater than 0 under both circumstances of a is between 0 and 1, as well as a is greater than 1. Here we continue to work on the alternative approach of example 1. In this approach, instead of finding the difference between the two modulus logarithmic expressions, we try to find their ratio and see if the ratio is greater than or less than 1. Based on the given criterion, since x is between 0 and 1, then 1 plus x is between 1 and 2, while 1 minus x is between 0 and 1. Hence, the quotient of the modulus of logarithm base a of 1 minus x to the modulus of logarithm base a of 1 plus x equals the modulus of logarithm base 1 plus x of 1 minus x, which equals negative logarithm base 1 plus x of 1 minus x. After further simplifying the expression, the ratio equals logarithm base 1 plus x of the quotient of 1 plus x to 1 minus x squared, or in parentheses, which is greater than logarithm base 1 plus x of 1 plus x, which equals 1. Hence, we have proved that the ratio is greater than 1. Therefore, we may conclude that the modulus of logarithm base a of 1 minus x is greater than the modulus of logarithm base a of 1 plus x. Example 2 is to solve an inequality logarithm base 2 of x plus 1 over x plus 3 or in parentheses is less than or equal to 3. According to the given inequality, the right-hand side number 3 can be written to logarithm base 2 of 2 cubed. Based on the logarithmic laws, we have two simultaneous inequalities to satisfy here. Since the base of the logarithmic expression is 2, which is greater than 1, the base argument of x plus its reciprocal plus 3 is less than or equal to 3. On the other hand, the base argument itself must be greater than 0. After factorizing both inequalities to their factorized form accordingly, we may proceed to solve them and obtain the results of x value range accordingly. After intersecting their value range, we find the x is the union of the two sets. One is between the negative sum of 3 and square root 5 over 2, and the sum of negative 3 and square root 5 over 2, excluding both endpoints. The other one is between 5 minus square root 21 over 2 and 5 plus square root 21 over 2, including both endpoints. The question in example 3 is to find the value range of a, given that its satisfied inequality of logarithm base a of 2 is greater than logarithm base 2 of a, where a is greater than 0 but is not equal to 1. After the base of these logarithmic expressions being changed to e, logarithm base a of 2 equals the quotient of natural logarithm of 2 to natural logarithm of a, while logarithm base 2 of a equals the quotient of natural logarithm of a to natural logarithm of 2. Based on the given inequality, we have the inequality of the quotient of natural logarithm of 2 to natural logarithm of a is greater than the quotient of natural logarithm of a to natural logarithm of 2. From this point, we need to discuss the value range of a to further proceed with this inequality. First, when a is between 0 and 1, then natural logarithm of a is less than 0. So we have two simultaneous inequalities to satisfy here. The first one is natural logarithm squared of a is greater than natural logarithm squared of 2. The second one is a is greater than 0 but is less than 1. After factorizing the first inequality, these two simultaneous inequalities being solved, and the value range of a is obtained, which is between 0 and half, not including both endpoints. Here we continue to work on the alternative approach for example 3. When a is greater than 1, in this case, natural logarithm of a is greater than 0. Hence, we have two simultaneous inequalities established here. One of them is natural logarithm squared of a is less than natural logarithm squared of 2. The second one is a is greater than 1. After transforming and simplifying them based on the logarithmic laws, the value range of a is obtained, which is between 1 and 2, not including both endpoints. Based on the above, we may conclude when the value range of a is the union of two sets, one is between half and 1, and the other is between 1 and 2, excluding odd endpoints, the inequality is valid. Example 4 presents a logarithmic function fx, which equals x squared plus common logarithm of a plus 2, or in parentheses times x, plus common logarithm of b. where x is a real number and f -1 equals -2. The question is to find the sum of a and b given that fx is greater than or equal to 2x. Since f -1 equals -2 and f -1 can also be expressed to 1 minus open bracket common logarithm of a plus 2 close bracket plus common logarithm of b, which equals -2. After simplifying this equation, we have the relation of common logarithm of a minus common logarithm of b equals 1. Since fx is greater than or equal to 2x, it can be simplified to the quadratic inequality of x squared plus common logarithm of a times x plus common logarithm of b, which is greater than or equal to 0. Since the quadratic coefficient is greater than 0, as long as its discriminant is less than or equal to 0, fx will be greater than or equal to 2x. After including the early established relation of common logarithm of a minus common logarithm of b equals 1, we calculate the common logarithm of b equals 1 and the common logarithm of a equals 2. Hence, b equals 10 and a equals 100 accordingly. Therefore, a plus b equals 110. Example 5 presents a logarithmic function fx which equals x squared plus common logarithm of x plus 1, where fx is an odd function and x is greater than 0. The question is to find the root of fx when x is less than 0. Since f negative x equals negative fx and x is greater than -1, so when x is between 0 and 1, fx equals x squared plus common logarithm of x plus 1. This is equivalent to when negative x is between -1 and 0. So f negative x equals x squared plus common logarithm of 1 minus x. If we assume y equals negative x, then fy equals y squared plus common logarithm of 1 plus y, which is equivalent to fx equals x squared plus common logarithm of x plus 1. Hence, when x is between -1 and 0, excluding both endpoints, fx equals x squared plus common logarithm of x plus 1. Example 6 presents a hybrid function of fx. When x is less than 1, fx equals 3a minus 1, or in parentheses times x plus 4a. When x is greater than or equal to 1, fx equals logarithm base a of x, given that fx is a monotonic decreasing function within odd real numbers. Based on the above, the question is to find the value range of a. Since fx is a monotonic decreasing function, its derivative must be less than 0. Hence, we find the derivative function of fx so that x is less than 1. Now, f prime x equals 3a minus 1 when x is greater than or equal to 1. F prime x equals natural logarithm of a over x. Therefore, we have two simultaneous inequalities to satisfy, and one of them is 3a minus 1 is less than 0. The other one is natural logarithm of a is less than 0. After solving these two inequalities, we obtain the value range of a, which is between 0 and 1/3, excluding both endpoints.
If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.